for the invitation. It is a great pleasure to talk about my work with all of you and get your comments and feedback. Today I want to talk about Hawking radiation and entanglement. In part of the invitation, it is a great pleasure to talk about my work with all of you and get your comments and feedback. Today I want to talk about Hawking radiation and entanglement. In part of the invitation, it is a great pleasure to. Do you hear the echo?
Yes, everything is okay, I think.
I was hearing myself repeated. Did you hear that?
Yes, I heard some echo, but now is not there, I think.
Okay. It was very weird. It was myself speaking again. I was saying that I'm going to speak about entanglement production in the process of Hawking radiation. And of course, this is not a new topic. A lot has been said about it. My goal is to contribute to this phenomena by bringing in tools from Gaussian quantum information, and to show you that with these tools, first of all, many old results can be derived in a very easy and simple manner, but also new aspects unknown to me can be revealed and clarified. So hopefully you will benefit from these tools. And also, because this is a long talk, I'll make an effort to be pedagogical, particularly because the talk is recorded and students can watch it afterwards. So I think trying to be as pedagogical as possible will be beneficial for many people. And I apologize for the experts in the audience who may feel some aspects of the talk are a bit elementary. Anyway, let's go over business. So let me start with a motivation. I don't think this gentleman needs any introduction in this community, and neither does his one of the most celebrated results among many, that black holes radiate as hot black bodies and evaporate. Hawking itself presented in a pictorial or heuristic manner this effect by saying that an event horizon is able to break apart vacuum fluctuations, break apart pairs of virtual particles in such a way that one of them may escape to infinity, while the other will go into the black hole and the singularity eventually. And he showed us that the outgoing particle carries energy and is in a thermal state with a temperature given by the Hawking temperature, which has this expression for Schwarzschild black holes. And because this is a mixed state, we know today that this particle must be quantum entangled with this other particle. So the black hole loses mass, but it also gets entangled with the exterior. Of course, this picture is very heuristic for many reasons, as you know. We know today that an actual event horizon is not really needed. A apparent horizon or a dynamical horizon will do the job. And also that, in quantum field theory, the notion of particle in the region near the black hole is not defined unambiguously. And also, as I will discuss later, that even the relation between what the partner mode is of the Hawking particle and where the energy goes is different. That the field mode carrying the information is not always the same as the field mode carrying negative energy. So this picture is very heuristic, but we will see these details during the talk. So what I want to answer in this talk is how much entanglement is generated during the Hawking process. So that is essentially the question I want to ask. And the answer will be that it depends. Of course, it will depend on the mass and the spin of the black hole. That is quite natural because the Hawking temperature depends on these parameters. Although for spinning black holes, you will see that there is an additional source of entanglement associated to the ergoregion. So not only with the horizon, but there is a second source of entanglement. Spinning black holes are quite interesting in that aspect. But I will also show you that it also depends on the environment. That a black hole immersed in a thermal bath generate different entanglement that they would do in isolation. And the goal of this talk is to clarify all these points. So in this sense, the entanglement generated in the Hawking process is actually tunable. You can tune it, putting the black hole in different environments, and I will discuss how that happened. At the practical level, what I want to do is to quantify entanglement in the Hawking process. So let's go over it. Of course, I am not the first one trying to do this. Absolutely not. And the most famous and interesting result was derived by Page in 2013. And what Page did was quite simple and interesting at the same time. Page essentially computed the entropy of the radiation reaching future null infinity. He didn't care about the modes inside the black hole. He just computed the radiation, the entropy of this radiation, which is thermal, modulated with gray body factors that he knew very well from his previous calculation. And then he argued that entropy, because the total state of the field is pure, is the in vacuum, then that entropy quantifies the entanglement between the Hawking radiation and whatever other part of the radiation that goes inside the black hole. That is called entanglement entropy, and in this situation is a quantifier for entanglement. And this is what he did. And this is very interesting. And however, the limitation is that this only works for whenever the state is pure. Because if the state is mixed, then the entropy of the radiation, of part of the radiation, the entropy of a subsystem, is not anymore a quantifier of entanglement. Doesn't quantify entanglement because the state itself has entropy. So therefore, this only works for black holes in isolation. And the truth is that this is not satisfied by any black hole we know in nature, because in the sky, all black holes are within a thermal bath given by the CMB radiation. So I was curious to see what happens when you put the black hole in different environments. And for that, one needs to go beyond entropy, and one needs to account, to describe the modes inside and use other quantifiers for entanglement. And that is what I will do. Before going into that, you need to allow me to do a pedagogical excursion because I'm going to introduce in a pedagogical way some of the tools I'm going to use. And this is the pedagogical part of my talk that I mentioned before. So this is a kind of elementary tools, but they are not always familiar to people in the gravity community. So I apologize if you know this well, but maybe beneficial for others. The tools are tools for Gaussian quantum state for bosonic systems of finite dimensional quantum systems. So Gaussian states for finite dimensional bosonic quantum systems. And a good reference, which is quite useful, is given by this recent book by Serafini. These are new tools and very popular tools in quantum info, quantum optics community. So what I am trying to do is to adapt them to these gravitational situations, gravitational particle production. So very quickly, imagine you get a system with n bosonic degrees of freedom. So you have n pairs of canonical variables. And I'm going to put them together in a vector I will call R with an index I that runs from 1 to 2n. Because in this way, I can compactly write many things. For instance, the canonical commutation relations take this simple form, where this is a 2n by 2n matrix given by n copies of this symplectic matrix. Then what you need to remember is that a Gaussian state, pure or mixed, doesn't matter. It is completely and by definition and uniquely determined by the first and the second moments of the state. By first moments, I mean the expectation value of any of these canonical operators individually. And by the second moments, I mean the expectation value of products of two of them. So these two quantities, mu I and this matrix ij, contains all information about the state. Any other prediction can be obtained from them. However, instead of working with these second moments, it is more efficient just to focus on the symmetric part, because the anti-symmetric part is fully determined by the commutation relations and does not contain information about the state. It's state independent. Only the symmetric part depends on the state. And it's also good to remove the first moments. So rather than this, it is better to work with the symmetrized and centered second moments. The symmetrized and centered second moments is what is called the covariance matrix. And the statement is that these first moments and the covariance matrix, which is a symmetric 2n by 2n matrix, encode all information about the density matrix of the state. But they are way more handy because this is a vector of 2n components and a symmetric matrix of 2n by 2n. And to give you an example of how handy this is, if you give me a Gaussian state given by a vector and a matrix, and you ask me, and you make a partition of the system in two subsystems, and you ask me to compute the reduced state. The reduced state of a subsystem of these variables is also Gaussian, and the mean, the first moments, and the covariance matrix are just given by the corresponding piece of the full first moments and the full covariance matrix. So it is super simple to compute the reduced quantum state without the need to take any trace in the Hilbert space or anything like that. It is just handy. Also, if you ask me about the number of quanta in one of the modes A, this simple expression, the trace of the reduced sigma, and this expression where NA is the number of modes in subsystem A, give you the result. I show this just to show you an example of how handy these tools are. Many results can be obtained in a very straightforward manner. And I will use this later on for Hawking radiation. Examples, vacuum is Gaussian, coherent state, squeeze states, thermal states, all these states are Gaussian, and the vacuum has a mean 0, and the covariance matrix is the identity. A coherent state is a displaced vacuum in the sense that it has the same second moments, same covariance matrix, but a displaced first moments. As a squeeze state, the covariance matrix is just squeezed in that way, one quadrature and the other in different directions. This is for a single mode. If you have many more modes, you just generalize this. Thermal states, the covariance matrix for a single mode is just proportional to the identity and with a factor larger than 1 for a single mode. If you have many modes, you just have, the direct sum of these matrices. And because, this is for Gaussian states, of course, but most of the states we are interested in are Gaussian. So this will be useful. And, another interesting result that will be useful is that a Gaussian state is pure if and only if the eigenvalues of this combination are all plus minus I. And if you like geometry, in this situation, for a pure Gaussian state, this combination defines a complex structure in the phase space. And therefore, there is this relation between Gaussian states and color geometries, which I don't want to go into it. But if you like geometry, this is a very interesting connection, well known in the community, of course. What else? I want to talk about evolution. If the Hamiltonian of the system is quadratic, so we call this a linear system, then it happens that Gaussian states evolve to Gaussian states. Evolution preserves Gaussianity. So the evolution will change the initial mean and covariance matrix into a final means and covariance matrix. And because evolution is linear, these two sets of objects must be related by a matrix. Oops, sorry. So there is a matrix, I call it the evolution matrix, relating the first moments, initial and final, and second moments, initial and final. And one can also show that because linearity, this S matrix can be obtained just solving the classical equations of motion. In fact, this S matrix is made of Bogoliubov coefficients, which you obtain by solving the classical equations of motion. So this is extremely simple, right? And if you work with Gaussian states and linear quadratic Hamiltonians, then you don't need to work in the Hilbert space. You can forget about density operators, which are infinite dimensional, Schrödinger equation, unitary operators, and rather all the dynamics and all the discussion can be phrased with vectors in the phase space and a matrix, finite dimensional matrix implementing evolution, which is obtained from the classical equations of motion. So this is quite useful at the practical level, and this will apply to Hawking radiation, as I will show you in a second. Another tool I need to introduce is entanglement. I mentioned that entanglement entropy is only an entanglement quantifier when the total state is pure. Instead, I will use logarithmic negativity to quantify entanglement, which is useful for pure and mixed states alike. And it is defined in this manner. It is the trace norm of the partial trace. This is partial trace on one of the subsystems, Bob or Alice, one of them, and then take the log, and this is the way you define it. And it has interesting properties, which I'm not gonna describe, but you can read them here. So this is what I will use to quantify entanglement in general. It reduces essentially to entanglement entropy when the state is pure, but it goes beyond when the state is not pure. So just to finish this brief introduction, let me give you two handy examples of Gaussian evolution, which I will use a lot later on. One is a very simple example, just two modes evolving to two modes, and this is what people in optics call a beam splitter. And it is just this transformation, phrase using creation and annihilation operators. The in operators evolve to out operators, and the out one is just a combination of these two annihilation operators. And this other combination for the second one. So this is just a rotation of annihilation operators, and there is no mixing of creation and annihilation. So only annihilation in these two equations. So just a rotation. The S matrix of this transformation is just a rotation, as you can see here. And, the physical effect of this transformation is just divide the incoming beams. So the incoming one mode gets partially transmitted, partially reflected, and the same for the other one. And this cosine and sine have information about the transmission and reflection coefficients. So this is what describes, for instance, scattering by a potential barrier in standard quantum mechanics or even in field theory. Simple beam splitter. And I will use this symbol to describe it later on. And this is a passive transformation because there is no mixing of creation and annihilation operators, and that means that the vacuum remains invariant. This is why it's called passive. And there is no generation of entanglement. This is just a scattering process, simple scattering process. The second example is different. Is what people call a two-mode squeezer, and by definition, the out operators are a combination of the in and the in dagger operators. This is just an example. This R is called the squeezing intensity. I could also include a squeezing angle, but just for simplicity in this presentation, I don't. But the most general two-mode squeezer will also have an angle, a phase here. But it's not important for this discussion. And this two-mode squeezer, if you want to see what it does physically, we can act on it on the vacuum. So imagine you have a two-mode system in the vacuum, so 0 and identity, and you act with S. You get 0 for the mean, but the covariance matrix, which is S sigma in S dagger, is now different from the identity. So the final state is different from the vacuum. And this is the covariance matrix of each of the subsystems of mode A and mode B. And you can see it is a thermal state. It is proportional to the identity with a proportionality factor larger than 1. So each mode is in a thermal state and they are correlated. These off-diagonal terms indicate correlations. And these correlations contain entanglement. So you can compute log negativity, and the log negativity is given by this expression determined by the squeezing intensity of the two-mode squeezer. So I'm going to use this symbol to denote a two-mode squeezer. Sorry. And what we are obtaining here is that if you put the vacuum initially, the final state, each mode is in a thermal state and they are entangled. And this state is called a two-mode squeeze vacuum. The final state is normally called a two-mode squeeze vacuum. Okay, these are the tools I wanted to introduce. So if you were sleeping, now you can wake up. And now I'm going to talk about the Hawking process. So the question is whether if we can apply these tools to quantify the generation of entanglement in the Hawking radiation. And that is not obvious because in Hawking radiation, we deal with fields, which are infinite dimensional as mechanical systems. And so in particular, that is quite obvious if you go to Hawking's paper. Hawking took an out mode, which is a positive frequency mode in scribe class, propagated back in time, and he decomposed it in modes and realized that a single out mode gets contribution from all in modes, infinitely many. Therefore, this seems an infinite dimensional problem, and the tools I just presented do not have an obvious application because infinitely many modes are involved. But you may wonder whether it is possible to diagonalize this evolution to change basis for the in modes in such a way that the out mode is coming just from a single or a couple of in modes instead of infinitely many. And the question is yes. And in fact, this was sorted out soon after Hawking's paper by a paper by Bob Wall, and this part of the paper didn't get much attention, but I think is quite interesting and quite deep, and as I will describe now. So the question is the following: consider I'm going to describe part of the content of this paper. So consider a Hawking mode reaching scribe class. I'm going to call this up mode. And for a second, I'm going to forget about backscattering. I will introduce it later. So really, this is a wave packet centered on some frequency omega, and it is in a mixed state as Hawking computed, thermal state, and when the state is the in vacuum. So we want to find the partner mode, the Hawking partner, and the partner mode is another mode which purifies this Hawking mode, in the sense that the two modes together are in a pure state. So it's the quantum partner in that purification, purifying sense. And I'm not going to describe that, but one can show that this partner, when the state of the field is pure, it exists always and is unique. It's a unique partner mode. Up to system local symplectic transformations for the experts in the talk, in the audience. The partner was identified by Wald 40 years before or 30 years before the notion of partner mode in field theory was established. So that was quite interesting. And the way of identifying it is you need to bring the up mode to scribe minus, reflect it across VH, which is the position of the event horizon as seen from scribe minus, and then complex conjugate. And one can show that these two modes are in a pure state. So this is the purifying mode. I don't show why, but you just need to believe me or go to Wald's paper and see the proof. So this is the purifying mode, and furthermore, Wald proved that if you take this combination of up and down conjugated, and vice versa, down and up conjugated with this concrete factor, this is the crucial factor here, this exact linear combination, and then normalize it. These two modes, this combination have only positive in frequencies. They are made only of positive frequency modes in scribe class. So therefore, what we have to do to simplify the calculation is use a basis of modes in scribe minus given by these modes, one for each omega, where omega labels really is a label of the out mode they will produce. Sorry. They will produce these modes, of course, one for each omega, L, and M, define the standard in vacuum because they are made only of positive frequency modes. And for the out basis, use pairs of up and down, and dn. By the way, I didn't mention, but dn, the name is used as a reflection of up. If you reflect it, you get dn. And just to remind us the way we obtain this partner. And this is what some people call the Wald basis, and as I will show you, it makes the calculation quite straightforward. And also, I just wanted to mention that notice that the partner mode enters the horizon, very close to this last ray VH, very close to it. And here, for a general collapsing process, the energy momentum tensor here is essentially zero. In particular, if you consider Baidea solution, a Baidea process of collapse where the matter producing the black hole is this null shell of radiation, the energy momentum tensor here is exactly zero. This is Minkowski spacetime in the Baidea case. So you see here clearly an example where the partner modes carry no energy at all because the partner modes, the energy momentum tensor here are exactly zero. So this tells us that even in this simple scenario of Baidea, that the flux of information and the flux of energy they are not the same at all. And one should separate them in all discussions. The information here enters the horizon in a region where the energy momentum tensor is zero. And something very similar happens if you consider a star collapsing rather than I just wanted to emphasize this point here. Okay, let me come back to Wald's basis. Now I want to compute Hawking radiation. What Wald's basis is telling us is that the process of pair creation can be understood as the evolution of two modes to two modes. And in this sense, we have diagonalized the evolution, two modes to two modes. And therefore, sorry. And in fact, if you do the calculation, which is just rephrasing the calculation in Hawking's paper, you realize that these out and up down modes, the end modes, are just related to the in modes in this particular manner. Cosh of RH and the second dagger, sinh, and vice versa, where this RH is given by this expression, where TH is the Hawking temperature. So the evolution from these two modes to these two modes is exactly and precisely a two-mode squeezer, the one I described before. So in this language, again, this is just a rephrasing of Hawking's calculation. But this makes evident that the process of pair creation here is a two-mode squeezer originated from the event horizon, so to speak. And therefore, if you start with the vacuum, the final state is a two-mode squeeze vacuum in which each of the modes is in a thermal state and they are quantum mechanically entangled. Phil, if you have a question, go ahead.
Philip, please ask your question.
Yes. Does it really depend on black holes, or is it just a case of any geometry with a minimal surface?
It appears in many other circumstances.
I mean, it seems there's no dynamics of black holes involved here.
I mean, there is dynamics in the sense that we are using the out basis knows about what is natural in a Scri class, is what we call a particle there. This is why we choose these out modes to begin with. If there is no dynamics, then this squeezing intensity is zero, and the vacuum evolves to vacuum. So dynamics enters into what is the natural set of modes to choose at the future, and then the relation between in and out is non-trivial in this case.
Oh, okay, thank you.
And in particular, this squeezing intensity knows about the mass of the black hole via the Hawking temperature. Okay, so now let me include the backscattering. So we have described that these two modes, the initial vacuum goes to a two-mode squeeze vacuum, but now the out mode needs to make it up to infinity, and there is a potential barrier here, which I draw here as a line, but it's not actually a line, it's an extended object. So this up mode needs
I'm sorry, one more question.
Please.
Deepak, please ask your question.
Yeah, just a clarifying question.
Sure.
Ivan, this description of pair creation at the horizon in terms of squeeze modes, like when was it real? Who came up with this idea first? Like who understood this? Was it you or somebody else? I mean, like, can you give me a reference?
It's a good question. No, I don't want to claim I was the first one. Maybe the first one in phrasing it in this concrete manner, but the results are implicit in many references, and I'm sure many people understood that, even they didn't formulate it in that way.
Okay, thanks.
So the fact that the particle creation is a two-mode squeeze process has been pointed out. I don't wanna claim I am the first one. So.
No, that's not.
So this up mode needs to, part will be transmitted, part will be reflected. So we need to describe this, and in fact, that is what we call backscattering. And in fact, the out mode can also be excited if you illuminate the black hole from the exterior, because part of this mode I call in mode will be scattered back, and you can excite the out mode. So we need to include this extra process to describe the full thing. But this process is just scattering by a potential barrier. And I mentioned before, this is exactly a beam splitter. So these up and in operators go to out and down, which are just a combination of, mixing a rotation of annihilation operators, where these coefficients, cos and sine, they have the information of the transmission and reflection coefficients of the potential barrier, and they were computed by Page. So to summarize, Deepak?
Ivan, one quick question.
Sure.
Where did this, we have the event horizon. Where did the barrier come from? What is this?
Is the potential, the potential gravitational and centrifugal potential barrier.
This is for a rotate. But
no,
so
even
this is
even
okay.
for a Schwarzschild black hole, if you take the Klein-Gordon equation and you decompose your field in spherical harmonics, there is a centrifugal barrier,
right.
on L, and also the gravitational part. It has the two parts. It is peaked at a radius equal to 3m, where m is the mass of the black hole for a Schwarzschild black hole, and that is what produces that part of the wave gets reflected and part gets transmitted.
Okay.
So the Hawking process can be described for each out frequency and L and M as an evolution from 3 modes to 3 modes. And this evolution is made of 2 different processes, a 2-mode squeezer at the horizon and a beam splitter originated at the potential barrier. And this is the concrete way these things relate to each other. So I write this picture as a circuit in which the 2 in modes suffer a 2-mode squeezing process, and then one of the legs gets involved in a beam splitter with the other in mode, and you get final. And so this is extremely useful because you can get a lot of results in a very simple manner just looking at this. In fact, as an example, just looking at this, I know that these 2 modes, the out and down, are not entangled just by inspection, because they are not entangled before the beam splitter, and the beam splitter doesn't create entanglement. So I know that these are not entangled. However, I know that this blue mode is entangled with both down and out. Why? Because the outputs of the 2-mode squeezer are entangled, and then this beam splitter divides this beam in 2 parts. So this gets entangled with this, and this gets entangled with that, just by inspection, to give you an idea of why these things are kind of useful. But even more, one can put numbers and one can write the covariance matrix of this process, which is just the covariance matrix of a 2-mode squeezer, cos, sine, and cos, and the covariance matrix of a beam splitter, cos, sine, and cos. In the right order to involve the appropriate modes. You multiply them and you get the whole covariance matrix of the circuit. And now if you give me an in state, I just need to do matrix multiplication to compute the out state. And from this out mean and covariance matrix, I can derive all the properties: entanglement, particle number, entropies of every individual mode, etc. So this becomes a simple, extremely simple calculation, just matrix multiplication. So example, imagine I give you the vacuum, 0 and identity covariance matrix. The out state has 0 mean and covariance matrix by this multiplication. If you compute the particle number in the out mode using the expression I gave you before, you get cos squared sine squared. But this is just the gray-body factors divided by the Planckian factor, which is this sine. If you use the expression for R I gave you before, so did you recover the Hawking's result in a very simple manner. If you want to compute entanglement, I show you here the analytical expression for the entanglement between the mode escaping and the two modes inside the black hole, and it's given by this expression. You can compute entanglement between any single mode. This is just an example of a partition of a special interest, interior-exterior. If you use a coherent state, you just need to change the first moments, and if you compute the particle number, you will get the same as before, plus an additional contribution. And this is what we call a stimulated Hawking radiation. More particles have been produced because the initial state is not the vacuum. However, you can check that the entanglement is exactly the same as before. So in this situation, this stimulated radiation does not create additional entanglement. Imagine you put the black hole in a thermal bath. So if you put the black hole in a thermal bath, then the initial state should be a thermal state. And out of the three modes, I'm going to populate thermally only this in mode. And I'm going to put these two in the vacuum. Why? Is because these two modes are, the frequency of these modes is super high, is close to be Transplanckian. Therefore, unless the temperature is of the order of the Planck scale, it is a good approximation to assume they are in the vacuum. However, this is a low frequency mode the frequency is the same as the Hawking mode, because in this region, the space-time is static, so frequency is conserved. So let me assume this mode is in a thermal state. Ali, go ahead. Ali, you have a question?
Yeah, sorry, sorry, my microphone was not working.
Okay.
So I just have a quick question. So these two modes you said are Transplanckian. I had thought they are the in modes, and I thought you argued a little bit ago that they have some kind of zero energy. So I'm a little confused whether they have very high frequency or they have zero energy.
Right. They have high frequency, but they are they have high frequency, but if we assume we trust quantum field theory for those frequencies, they are in the vacuum. So the modes have high frequency, but they are not populated initially. They are put in the vacuum. So the two things are compatible, having zero energy momentum tensor and the mode itself be high frequency. So the two things are compatible. It's like in a harmonic oscillator, you can have whatever frequency you want for the oscillator, but you can set up the system in the vacuum state. The two things are compatible.
I see. But this means that there are all the possible frequencies. They are also here in going because you don't need them to be populated. So just all the frequencies are here.
Exactly. All the frequencies. Exactly. All the frequencies are there. But I am focusing on the frequencies, on the modes which are the progenitors of a Hawking mode. So I fix a Hawking mode and I just focus on the two progenitors. And I do that for every single Hawking mode. This is why I am talking only about two modes now, even though all of them are present. I am separating the whole discussion in pieces like this.
I'd like to discuss this more, but I'll let you finish so that.
Okay, great. Thank you. Thank you. We can discuss more, absolutely. So what happens if you have a thermal state? Well, if you just do the calculation the way I described, and you compute log negativity, entanglement between exterior and exterior. This is for a single mode, single omega, L and M. And I am choosing here the mode carrying most of the energy, the peak of the energy spectrum. What you see here is that this is as a function of the temperature of the environment in units of the Hawking temperature. You see here that as soon as the environment gets hotter, is hotter than the black hole itself, the amount of entanglement decreases drastically and reaches a plateau which is about 90% reduction compared to the initial thing. So this is telling us that the mere presence of thermal radiation around the black hole inhibits the generation of entanglement. The black hole is still emitting pairs. Of course, it also gains a lot of energy from the radiation outside. But the pairs are still emitted, but they carry way less entanglement than they do in isolation. So black holes in the sky, they emit 90%, around 90% less entanglement than they would do in isolation. Nevertheless, they still emit entanglement. So that is the second message. So even though the black hole does not evaporate because it gains more energy than what it loses, it creates some entanglement. So even a growing black hole is getting more and more entangled with time, with the environment, and it's kind of interesting. So now let me just show you the same plots. Summing, here I am summing over L and M and computing the flux of entanglement per unit time and per unit frequency. And it has this form for 0 temperature environment. And as you increase the temperature of the environment, this curve goes down. And this is for environment 10 times hotter than the Hawking temperature. And this second plot is the same, but I am also summing over frequencies. So this is the total entanglement flux reaching Scribe plus as a function of the temperature of the environment. And you see this suppression of entanglement generation as the environment gets hotter and hotter. Okay, now let me discuss what happens when you include rotation. And so when you include rotation, the difference is that this region, including the potential, now is an ergoregion. There is an ergo surface, and this region is an ergoregion, and that changes some aspects of the emission quite a lot, in a quite interesting manner. So in this situation, one needs to distinguish between super radiant modes, which are defined by modes whose frequency is larger than the product of the azimuthal, the magnetic angular quantum number, and the angular velocity of the horizon. This is what this quantity is, angular velocity of the horizon. When this happens, we call this non-super radiant modes, and then the evolution is, for that mode, is the same as in Schwarzschild, qualitatively, in the sense that we have a two-mode squeezing process associated to the horizon, and then a scattering process at this passive transformation here. An active transformation generating particles and entanglement, and a passive transformation. But that changes radically for super radiant modes. For super radiant modes, what happens is that essentially, the key point is that the Klein-Gordon norm, or the symplectic norm of modes within the ergoregion, flips sign. It was positive here, it was negative here. And I indicate that in this picture by replacing a dn dagger by a dn, trying to emphasize that is because it has changed norm. The same for the up mode and the same for the down mode. So these three modes change norm, but that changes the character of this scattering. That simple fact, this mathematical fact, changes the character of this scattering because now this scattering mixes A's and A daggers. Here, this scattering doesn't mix A's and A daggers. A's go to A's, but here A's and A daggers get mixed, and therefore this becomes an active transformation. It's not a beam splitted anymore, it is a squeezer, two-mode squeezer. It creates entanglement, and it creates particles from the vacuum. So this is the radical change. And the fact that this is a two-mode squeezer, coming back to the question before, I never, for the horizon, I never saw the sentence clearly, but for this, there is a old paper, which I think went unnoticed. And I learned recently about it. I didn't know it until recently. And they mention explicitly that this acts as a squeezing process. So they noticed that before I did. Maybe not with this language, but so in this case, if you want the scattering matrices for non-super radiant modes, you just need to multiply a squeezer and a beam splitter. For super radiant modes, the beam splitter becomes also a squeezer. So this cos sign becomes cosh and sine, and they are larger than 1. At least the cosh is larger than 1. So the cosh is larger than 1, indicating, super radiant scattering classically and particle creation quantum mechanically. Abhay, go ahead, please.
Yes, please ask question.
Yeah. So the quick question was really about the even if I had just a star, stars have can have ergospheres if it is very rapidly rotating, and so there is no event horizon. And so, long time ago, I think in '70s, I pointed out that such stars would also have this radiation, the Hawking type radiations and something like that. So I think that is quite compatible, right? In that case, there is no squeezer at the horizon, but you still have a squeezer at the ergoregion. Is that correct?
Absolutely. Exactly.
Right.
Thank you. This is why I wanted to.
Excuse me, there is one more question by Philip. Philip, please ask your question.
Yes. You might be just about to discuss this, but can you go forward one slide? Yes. You didn't discuss what happens when omega equals omega, when W equals m omega h. I'm just wondering if S total becomes singular at that point.
No, it doesn't. It doesn't become singular because if you see each of them separately, they become singular, but the product becomes well defined.
Okay, thank you.
Let me answer Abhay's question. This is why I separate them precisely because there are situations in which you don't have the horizon squeezer, and Abhay just mentioned one example. But even if you don't have a horizon, as long as you have an ergoregion, you are going to have particle creation and the vacuum.
That's exactly what I had pointed out. But I think I certainly did not have the interpretation of a squeezer, but we had clear interpretation that there is actually particle creation, and therefore just quantum mechanically, the ergoregion would evaporate, just like the black hole evaporates. The ergoregion of a star also evaporates. That's what I had pointed out. Okay.
Thank you. This is useful. Thank you. And also because this tells you that even in the streamal case where the Hawking temperature goes away, you still have this process, which is
exactly. Thank you.
Thank you for pointing out that reference. I should take it into account. Observations, just repeating what I said. The ergoregion is a source of entanglement, just like the horizon is. However, there are important differences between the ergoregion and horizon squeezers. The ergoregion squeezer does not have a temperature associated to it. If you see the spectrum of particles, it's not black body radiation. Still, it emits particles, but not with a black body spectrum. And also is that the ergoregion squeezer is not in isolation, at least when there is a horizon, because it's stimulated by thermal radiation coming out, sorry, that's a typo, out from the horizon. Let me go. The horizon illuminates the ergoregion with thermal radiation, and that is going to inhibit a little bit the entanglement it generates, because the presence of thermal radiation degrades the amount of entanglement emitted. So the total process is a quite interesting interplay between two different squeezing processes. one associated with the the horizon, Hawking's process, and another different associated with the ergoregion. And here I just show you a few plots. I do it for photons and gravitons, which are the dominant channels for massive, macroscopic black holes. And I also sum for frequencies L and M. This is again entanglement exterior, interior for different spins of the black hole. This is an extremal black hole. This is a Schwarzschild limit for different temperatures of the environment. The top line is maximum emission, whenever the environment is the vacuum. And of course, there is more emission of entanglement the faster the black hole spins. And as you increment the temperature of the environment, the entanglement production gets smaller and smaller, as I mentioned before. In this plot, I separate the contribution of entanglement carried by non-superradiant modes and superradiant modes as a function of the spin of the angular of the black hole. For low spins, non-superradiant modes carry most of the entanglement. In particular, for Schwarzschild, there is no superradiant modes, so everything is non-superradiant. But whenever the spin gets really high, beyond 0.9, superradiant modes dominate. So these are the two messages. Thermal environments degrade entanglement, and entanglement in superradiant modes dominates for larger spins. And now I'm going to show you this plot. This plot is just entanglement between out and down mode. And I show you this because this entanglement can only be produced by the ergoregion. This entanglement cannot be produced by the horizon. So this entanglement is exactly zero in the Schwarzschild case. But whenever you have a spin, you can see that entanglement is different from zero. And I think that is an interesting calculation just to distinguish the two phenomena. So entirely coming from the ergoregion. So messages, entanglement between out and down cannot be created by the horizon. The ergoregion is, this shows that the ergoregion is a source of entanglement, even when it is illuminated by thermal radiation from the horizon and also from the exterior. So that degrades the entanglement produced by the ergoregion, but doesn't kill it completely. And for black holes spinning very fast, this source of entanglement actually dominates. The total entanglement is dominated by this entanglement. And just to finish, this is just same plot, total entanglement, exterior, interior, but distinguishing gravitons and photons. And as it also happens with energy, and angular momentum, for entanglement too, gravitons dominate whenever the black hole spin goes beyond 0.7. And most of the entanglement in that regime is emitted in gravitons. And just the last minute, I want to say a few words about experimental verification of this. And I want to emphasize what Abai said before, that these conclusions, that the ergoregion generates entanglement, applies to any ergoregion, not only a black hole, not even only a star. Any system with a rotation having a ergoregion will produce that. Even more, to any superradiant process. Even superradiant is not rotational superradiance. It is another type of superradiance. That is also a two-mode squeezer generating entanglement and pairs of particles. Here I want to focus on rotational superradiance. And I'm going to use an analog system. This is the frame of analog gravity, because, this is where I think analog gravity is super useful because in analog gravity, you can simulate a quantum field propagating in an ergoregion. And with the advantage that you can measure all modes. You can measure the out modes, the modes inside, etc., and check whether there is entanglement or not. So I'm going to use a system made of polaritons. Polaritons is a weird word, but it's just quasi-particles made by combining an electron hole, electron and a hole in a semiconductor with a photon. They interact with each other and they form a bound state, a quasi-particle, and they describe a quantum fluid that can be put in a condensate. Igor, you have a question?
Igor,
No,
please ask your question.
finish. I will ask after you finish.
Okay. So I am collaborating actively with the group of Maxime Jacquet at LKB in Paris, and this is part of his group, Kevin and Killian, and this is where they have this polariton fluid, which is extremely cold, a few Kelvin, and the nice part of these fluids is that they can be put in a condensate, and their velocity profile can be tuned in a very specific manner. They just need to illuminate the condensate with a laser with the appropriate profile, and that will induce a velocity field on the condensate and also a density field. In this concrete configuration, this is density. So you see something which has rotational superradiance, is static. And this is the phase which has information about the velocity. The gradient of the phase is the velocity. So the velocity is circular. So this is a two-dimensional layer of fluid which is rotating. And here I draw the angular, the component of the velocity in the angular direction, and the radial velocity, and the speed of sound. And you see that this radius, below this radius, the fluid rotates faster than the speed of sound, and therefore this region is an ergoregion, and that is an ergo surface. There is no horizon because the radial velocity is very small, so there is no horizon anywhere. The black dot here is just because the density is very small. The ergoregion is around here, and because the ergo surface, and because there is an ergo surface, you can do the study of waves, acoustic waves propagating there, and there is superradiance, and the same predictions I said before will happen. This ergoregion will emit spontaneously from the vacuum pairs of waves, which are quantum mechanical entangled, and they are in both sides of the ergoregion, and measuring density, which they can do very, very. They can measure density and phase, and from that they can reconstruct the covariance matrix, and eventually, hopefully, confirm whether there is generation of entanglement or not. So these results are in this recent paper, Entanglement from Superradiance and Rotating Quantum Fluids. Is a recent paper where these are experimental pictures of the fluid. They haven't measured yet the acoustic perturbations, and that is the next step. But they have generated an ergoregion with no horizon. There is no horizon here. So I think this is a quite interesting field of research, which brings all the machinery I discussed before about particle creation in ergoregions, and brings it to a setting with could be tested experimentally. And with that, I'm going to finish, and then you can ask questions. So the message is that the Gaussian formalism and these symplectic circuits, I call them, are powerful tools to study pair creation. So one of my goals here are to promote and advertise these tools to compute any kind of particle creation process in quantum field theory. Hawking process, two-mode squeezer. Super radiance from ergoregions, also a two-mode squeezer. My goal has been to understand the structure, quantify and understand the structure of entanglement, and learn that entanglement is tunable, can be degraded if you put the system in a thermal bath, and can also be a tune-up if you put the system in a squeeze state, which I didn't discuss today. And I think this is interesting both conceptually and also at the experimental level. And I want to finish here.
Okay, thank you very much for your very interesting talk. We have a queue for the questions already. The first in the queue is Igor Valovich. Igor, please ask your question.
Thank you very much for the nice talk. I have a question and a comment. I would say the first part of your talk about Gaussian states and so on is very clear. But I would say that the derivation of the Hawking temperature and so on is unfortunately not so very clear. In particular, I would like to repeat the question which Philip seems already asked you. Do you think that the Hawking temperature and other properties are related with the presence of horizon?
Right. So the question is whether the Hawking temperature is related to the presence of horizons.
Yes.
That is a good question, which I didn't enter. Of course, in the calculation by Hawking, there is a horizon, and you can check that the temperature agrees, an event horizon. The temperature agrees with the surface gravity of the horizon. In that case, there is no doubt. The question is whether in cases where there is no event horizon, there is, for instance, a trap surface for a while, a dynamical horizon that forms and then evaporates, whether the Hawking temperature is gonna be related to the properties of the horizon. And I think in that case, the answer is yes. You can define a local surface gravity, and they are gonna agree. You can ask again whether we actually need a horizon to have a thermal emission, or we could also have, in some circumstances, a thermal emission of quanta black body spectrum, at least for a period of time, without having a horizon. And I think the answer is yes. And many people have pointed out before myself, including Baylock Hu, Matt Visser, Liberati, Barceló. They have clearly emphasized many times that you could generate, what are the conditions that you need to accomplish to have particle creation with a thermal spectrum, and a horizon is not needed. A horizon will do it, but it's not actually needed. So in that concrete situation, the temperature will not be obviously associated to the properties of the horizon because there is no horizon, but will be associated to the properties of the dynamical space-time happening in that scenario.
Okay. Thank you very much. I would like to add the following comment. We also consider it as in Arefьeva, the question about Hawking type radiation, how it depends on horizon or not. Our conclusion was that it depends not on the horizon and other things, but on the reference frame, on the system of coordinates. And we found a wide class of coordinates in which we have Hawking type temperature.
Yes, I agree. I agree with that.
Okay, thank you very much.
Okay, next question is from Ali Akil. Ali, please ask your question.
Thank you. Yeah. So first, thank you for the presentation. I first just want to say that I like this kind of approaches where, kind of bottom up. We start from things we know and we try to build on them rather than, assuming some crazy things and hoping it works. So I appreciate this type of approaches. So thank you for that.
Mm-hmm.
Then I have two questions. The first one is just about the superradiance. I have been looking into like a quantum description of superradiance, and I didn't find. I found the most people who work on superradiance would treat the scalar field as a classical field. So could you just suggest me one or two references where there is like a quantum treatment like you do here of superradiance?
Yes, perhaps quantum superradiance, you can see that in this paper.
All right.
In this paper, I agree with you. I agree with you. Superradiance is always thought, even classically, and my point is that superradiance also has quantum counterpart. The classical superradiance is just the stimulated effect, and I think that is well known. But the process also generates entanglement. Even the superradiant scattering, where you illuminate the system with some initial state, also generates entanglement, and it has quantum aspects on it. Of course, if you illuminate with a coherent state, which has a huge amplitude, all these quantum features are overshine, are eclipsed by the coherent state itself, and the state is essentially classical. But it is precisely a two-motor squeezer. This is where it is. So it has its quantum part.
Cool. Thank you. I'll look at the reference. My second question, can you go back to the temperature, or not the temperature, the entanglement, the logarithmic negativity figure in the Schwarzschild case?
This is Schwarzschild case with temperature. You want the expression or the
curve is okay.
Okay.
All right. So this is with an environment, with a thermal environment, right?
Exactly.
Right.
Or if you want this one, which is for every frequency and summing in modes and for different environment temperatures. Black, 0 temperature, and then increasing temperature.
I see. So the increasing the temperature of the bath decreases the negativity of the radiation.
Exactly.
I'm trying to have to quickly think of a quantum information theoretic understanding of this, and it's not very clear in my mind. Like, so
the let me see if I have the reason is
my only just to help you answering me, because my only worry or concern is that it's just because there's less entropy for the radiation because the evaporation is now slower. But still, if you wait for long enough until the whole evaporation happens, you will generate at least as much entropy or as much entanglement.
I haven't done the calculation.
Inside out.
I could be interesting to see. I bet it's not the case, but I haven't done the calculation. So you can just, one way of understanding is that you take a two-mode squeezer in quantum information, quantum optics, and if one of the lines is thermally populated, the amount of entanglement it produces it decreases. So and it decreases, and in fact, if you thermally populate both, this will produce 0 entanglement if the temperature of the environment is large enough. So you can completely kill the entanglement of a two-mode squeezer by thermally populating it. Entanglement is a subtle animal, and it's not that entanglement gets overshine. So it's there, but it gets eclipsed by other radiation. No, you can even kill it completely.
Yeah, I really need to see that because thinking about it now, like if I have two thermal states, and then the squeezing simply creates basically an entangled pair and sends one to each of the two systems. So I generate one entangled pair. I send each side of the pair to one of the two systems. The two systems get entangled. So I'm not saying it's not true. I'm just saying this is the reason why I'm curious to see the.
I invite you to do the exercise. Take a two-mode squeezer and put a thermal input in both channels, and you will see that there is a temperature, threshold temperature, beyond which the output is separable, not entangled. It's not entanglement is small; it's zero exactly, and that will make you realize how subtle is entanglement. But this is a longer discussion.
That's very interesting.
Maybe we should continue.
Yeah. Thank you.
Okay, I see more questions. There is a question from Norma Sanchez. Norma, please ask your question.
Hello, yes, thanks. I have a comment and a question. Whatever be your source, horizon or superradiant or other field, entanglement, the key point of entanglement is that it's always there. I mean, it's an intrinsic property of quantum. So the fact that you have an horizon or superradiant is, as I understand, to make an enhancement Now, my question, I assume you do agree with that. My question is, I would like to see the evolution of entanglement. I mean, in a realistic situation, because entanglement is assumed to do not be intense for any time. If I have two photons, for instance, the more easy case, and how much is this time?
But are you thinking about decoherence, that the entanglement will go away eventually, or?
Yes, decoherence.
Right, but decoherence, to discuss about decoherence, you need to put an environment and a concrete coupling between the system and the environment, and the answer will depend on that.
Yes, my question is if you have evaluated, I mean, a typical time for because you place it a thermal bath, you place it, I mean, you play with different cases, and a key point is how much the duration, I mean, the duration of time of entanglement, the duration in time of entanglement.
Right. So as I said, one could put an environment here and make a concrete model, but my point is that it really doesn't matter, because imagine imagine this red and orange mode are entangled, or red with the interior, the exterior radiation with the interior of the black hole. If this exterior mode interact with an environment but in such a way that this gets disentangled from this, the environment will get entangled with the exterior of the interior of the black hole. So the entanglement will be transferred from here to another.
But, I mean, you know that entanglement, I mean, in many of the problem in which entanglement is taken to place a role, how much time entanglement and the intensity of entanglement is there is important. I would like to see a plot with how much decoherence occurs in without the need to keep in continuously a source to get the entanglement. That I understand. I mean, if you have a source to get the entanglement, you compensate the decoherence, but the natural decoherence in time.
Right. I understand the question,
point.
right. I understand the question is an interesting question, but
that is a realistic, I mean, a realistic point.
Right. My only point is that if you want to know how much the black hole entangles with the exterior, this question is not relevant because...
No, but I am not looking on only for black holes because you mentioned, I mean, also the situation without black holes and so.
Right. Right. It's an interesting question in general. I agree. And thank you for the question.
And the other point, yes, excuse me. And the other point, I mean, it was a question by Igor on the horizon and the Hawking temperature. How much is horizon? If I understand the question, understood well, is horizon a necessary condition to get thermal spectrum? I mean, quantum. I should say that if you have vacuum and in the situation and you need and you want to get a thermal spectrum in space-time, you need an horizon. You do need an horizon. Now the question is that you can have global thermal equilibrium or not global, namely local thermal equilibrium. And that the types of horizon can vary, but you do need to have an horizon. And that is, you have for Rindler cases, that is uniform acceleration. Otherwise, of course, you can have a temperature, but you put something more than a space-time. But if we are talking about a space-time only, you need an horizon, whatever its type.
Thank you. Thank you for the comment.
Thank you.
Okay. I saw the questions by Abhay Ashtekar. Do you want to ask your question?
I can just, I can ask it. I thought it was getting late, so I raised lower my hand, but okay. Even I think this is kind of a little bit follow-up of what Norma was saying, that if I look at ergoregions, right? I mean, no star, no, I mean, the kind of experiment that you're doing in or let's suppose ideal thought experiment in which you just have a star with an ergoregion, but it's left alone. So there's no classical perturbation. But as in this old paper, the 70s paper that we pointed out that it would actually evaporate. The ergoregion will evaporate. So the star is just going to loses angular momentum and becomes static. It's stationary to begin with, and it will become static ultimately. Or at least it will lose it. It may not be static, but it will lose the ergoregion. So this, I think, is a very clean way of actually understanding this idea about purification, right? In the sense that now we don't have anything about is the singularity resolved, what happened, etc., etc. Space-time was always just topologically R4. We just had a star, and the star just is slowly. So it seemed to me that this is a very interesting example in which one could find out how the purification occurs, and therefore, in that sense, entanglement.
Thank you
for the comment. It's interesting. I agree, but I want to add something. The danger with these situations is that so imagine you assume this star is fully transparent in order to avoid adding any artificial ingredient that may mask the discussion. Then the ergoregion will emit pairs of waves, one going out, the other coming in. But the one coming in will eventually transition to from ingoing to outgoing, and will excite the ergoregion from the interior, and will stimulate further emission of pairs, and that is creating an instability.
Right.
So ergoregions with no absorption in the interior become unstable, dynamically unstable. The horizon provides. Sorry, go ahead.
Right. So it's unstable, and therefore it will disappear ultimately.
Right.
The star will slow down.
Right, but it will be an explosive process, and perturbation theory will get out of control very quickly. The horizon provides an absorption mechanism, but if you don't have a horizon, what you need is any kind of absorption mechanism in the interior of the star, that the matter will absorb the waves, because otherwise, it's an exponential instability.
But so you're just saying you just can't calculate anymore, or is it the state? I mean, okay, even if it's it is an explosive thing, you still I get something at infinity, and final state would again be pure because the initial state was pure.
Yes,
and then the star is so final state. So therefore, purity will be. I mean, the process. What you're saying is that process is complicated and may not be easy to do perturbatively. It would be not adiabatic at the end of this process. But still, it is going to be complete recovery of information. So it's something which looked thermal for a long time. It really is like the charcoal example of Don Page, right? It's going to look like thermal for a long time, except that in this case, what you're saying is that it is not just slowly cooling down, but something is more dramatic is going to happen. But ultimately it will be pure again.
I agree.
So entanglement will be lost. I mean, there will be no entanglement at that. Right?
I agree. Yes.
Thank you.
Okay, we have one more question from Deepak. Deepak, please ask your question.
Well, thanks, Ivan, for hanging around for so long. And I guess I'll keep my question brief. Is it possible to detect what do you call it? The squeezing of this squeeze light? Let's say that you have a black hole that is maximally rotating, and we know now that the sky is full of those, I think, which are close to being maximally rotating. And so assuming that they are emitting these squeezed photons, is there any hope for detecting those photons and then for measuring the amount they are squeezed by and use that as a probe?
Thank you for the question, because it allows me to clarify. One needs to distinguish between single mode, single photon squeezing, and two photon squeezing. What happens here is two photon squeezing. The squeezing is in a quadrature, in a degree of freedom, which is a combination of both. And looking just a single photon, you will see thermal radiation. The squeezing is in between. It's in the relation between them. That is different from taking a beam of light and squeezing that beam alone. That's different. Here is a two-mode squeezing, which is thermal population, each of them, and quantum entangled in a concrete manner. And so if you see what is coming from here, you will see thermal radiation. That's it.
I see. So I mean, if you look at the what's it called, the Wigner distribution for a single photon, you will not that does not exhibit this
exactly. It does not exhibit that. Right. The squeezing is in something in between the two of them.
Okay.
This is why if you have a real black hole, you cannot measure what is inside. You can never test this entanglement. This is why I find these analogs so interesting, because in these analogs you can actually measure what is inside and what is outside. You have the system in the lab, and you can measure that squeezing because you can measure both and then test that they are squeezed. This is why I think that those experiments are quite fascinating.
I mean, just a very minor comment. What the formulation that you have is basically allows us to relate Hawking radiation directly and write it in terms of quantum circuit language, basically.
Right. Yes, exactly. Exactly.
So I think it'd be very nice to explore, for instance, the Hayden-Preskel protocol and related approaches by Jeff Pennington and others, which are expressed in the language of quantum circuits. But they appear to be unrealistic because they're talking about individual qubits.
Right.
But if you can recast that same thing in the language of radiation,
bosons,
then you're making a more concrete link to what we see in the real world.
Thank you. Thank you for the comment.
Yeah.
Good comment.
Okay. More questions, please? If not, let's thank the speaker once again for very interesting talk. Let's thank all people who participate in discussion, asking questions and giving comments. So thank you very